Thank you, Professor Mascarenhas. Well, I'll start the presentation here. And this paper is a very interesting result that we had in our research. First of all, it's a very interesting theoretical result that we had. And I will show you here the steps that we followed to reach this interesting result. So I'll start talking about the problem of 3 Tesla MR images of the brain and what can we do with it. Also, then I'll talk about skull stripping and in homogeneity correction. And I'll show you that those two problems are very closely related. And then I'll show you a very interesting method that we developed to solve those two problems together. Then I will show you the results and the concluding remarks. What we have here is that in your left side, 2 Tesla MR image. We can see that comparing to a 3 Tesla MR image, the quality of is poorer in the sense of the amount of noise that we have in the image. It's much more noisy. But by the other hand, we can see here the effect of inhomogeneity. Inhomogeneity that it's much stronger in 3 Tesla MR images. What's inhomogeneity? It's like a shadow that we have in the image. That's a part of it is brighter and a part of it gets darker. So we have some problems. For the human eyes, there is no problem. We can see how to make the segmentation of the image. It's clear. But for the computer, this constitutes a very big problem. And as you can see, 2 Tesla images, when we make skull stripping by a well-known segmentation method, we have this result here. It's a good stripping. It has minor errors in the borders, but when we try to strip the 3 Tesla image, we have much more trouble here. We can see that the cortex of the brain, this region here, and also a part of the back and the cerebellum starts to it's not got in the skull strip by the skull stripping method. So we want to solve this problem. We want to make a good segmentation for both 2 Tesla, especially for 3 Tesla images that are it's a better technology. And the problem is, we can see here an image of the gradient of both images. 2 Tesla images, we can see that the cortex all around the brain is very well defined. It's a very strong gradient here. By the other hand, this strong gradient, it's not of the cortex, as we call the boundary between gray matter and the cerebrospinal fluid. It's the boundary between gray matter and white matter. That's why segmentation gets a wrong result here. And as you can see, this is the problem of the caused by inhomogeneity, and it's very closely related to this problem. Why? Here, this line here is we made intensity profile over this line here of the pixels that fall over this line. And here in this image, this is the original image that we got. We can see that the profile is starts with very low intensities, and here in this part, after the red dot, we have higher intensities. When we correct the image intensity, we have a somewhat flat, a flatter histogram. So that helps a lot to make the automatic segmentation by skew stripping methods. And we start to study how much does inhomogeneity affects skew stripping. That was the question. Well, we start to make some research about some studies that were done over this topic, and we could find some papers that evaluate the influence of skew stripping over inhomogeneity correction. So if we make skew stripping and then inhomogeneity correction, those papers here, they show that inhomogeneity correction have a much better results when we strip the brain first, when we don't apply inhomogeneity correction methods over the entire image, but just over the brain. But what about the other way, inhomogeneity correction affecting skew stripping? We found out that nothing was published about this topic. Nothing about 3 Tesla images, only about 2 Tesla images. And about 2 Tesla images, they say, oh, don't worry. Inhomogeneity correction doesn't affect that much skew stripping. But when we analyzed 3 Tesla images, we found out that that's a big problem, real trouble that we have. It's a very strong influence of inhomogeneity correction over skew stripping in 3 Tesla MR images. So we must make correction before stripping, but the other result is that stripping must be done before correction. So now we have a dependence problem. How can we solve it? The solution that I will present here, it's in the paper. That's the theoretical contribution of the paper, and now I'll show you a method that it's a practical contribution that we made. It's an iterative application of inhomogeneity correction and skew stripping algorithms. What we've done, it's not complicated. It's good not to be complicated, right? We want a very simple methodology to solve the problems. What we did is, first we have the input image, and we made a skew stripping. We apply a skew stripping method here, and we got the brain with wrong boundaries, and especially in the cortex region, and here in the back of the cerebellum. Then we compute the brain mask of this segmentation, and we delete it. Why delete it? Because we don't wanna lose any content of the brain. So we make a deletion of the brain mask and apply inhomogeneity correction over the deleted image. We can see here that a part of the image that doesn't belong to the brain is also included in this deleted image, and we correct it, but we reduce the space of the inhomogeneity correction method, and that's good. As we saw in the studies, the previous studies showed that inhomogeneity correction does a better work when it's applied just over the brain. Okay, but now we don't have the brain here, we have a delayed corrected brain. what should we do? Then we compute the complement of the mask of this brain here, the dilated brain, and combine the outside region of the original image with the corrected brain, and the result is here. We just add one to the other. This one we add to the complement of the original image. And then the last step, we apply skew stripping again. Why? Because now we have the brain area or the brain volume corrected, and a good correction of it. And the result shows that we have a much better result around the cortex and in the back of the cerebellum. I will show you some results in a while. And here I will show you I just want to talk a little bit about the algorithm. It's nothing more that we did in that I showed you in the images in the previous slides. But the interesting thing here to show you is that the skew stripping, the first skew stripping, then computing the binary image, deleting it, making the inhomogeneity correction. We can add a standardization method here. I'll talk about this in a while. And then we complement the dilated brain, the dilated and corrected brain, to make the skew stripping again. Okay, but this method can be repeated any times. Why? This should be important. Sometimes the inhomogeneity correction is not very well applied. We don't have a perfect result. Maybe you want to apply two inhomogeneity correct methods. You can apply here. You can use many different skew stripping methods. One to start the segmentation and one to finalize it. You can combine any flavors of those methods here in our approach. And the standardization here is very important because when we get the corrected brain, sometimes the intensities will be different from the original image. So we standardize it so we have intensities in the same space, or in a similar space. So they can be combined without any hard, strong border, false borders be created between them. And that's it. That's this step here is optional. Sometimes if you have 2 Tesla images, well, you can try to enhance the result. Maybe you don't want to delete it a lot. You can make a small deletion, for example, in those cases. And what we did, we worked with just one skew stripping method in our paper and 2 inhomogeneity correction methods. Here we show the ground truth of this mask, the perfect manual segmentation by a specialist. And here are 4 results from different approaches. The first one here is made by BET without inhomogeneity correction, brain extraction tool from FSL tool to MRI image processing. You can see here that the cortex of the brain was not it's wrong. It's not, the segmentation is wrong here. Also in the back of the cerebellum here and the back of in the posterior lobe of the brain. If we try just to correct the inhomogeneity before stripping by N3 method, and N3 is the only method that's able to do that because all other methods require the stripped brain to make the inhomogeneity. Why? Because they say that it doesn't matter in the previous studies that they did, the researchers. And this result shows that it really improved the result, but still part of the cortex here and the back of the cerebellum were not correct segmented. But in our approach that we call interactive screw stripping, we applied first BET, then we made the correction with N3, and then we strip it again with BET over the corrected image, and the result is much better. We have a minor part of the cortex here that was out of the brain mask, but almost everything is correct here. And we also applied BET with a method called reference voxel that is from we are the authors of this method too, and we have a perfect delineation of the cortex and also the cerebellum. I'm not telling you that N3 is worse than reference voxel. It's just a result, and I'll show you that sometimes N3 in the ESS framework is better than reference voxel, but other times reference voxel is better. The evaluation of the paper, we made a accuracy evaluation, and I'll show here that interactive screw stripping with BET and free BET sequence was the better had the better accuracy over almost all images except for the second one here, the image number 1. And this result is statistically significant. This one over this and this. So it's really it is better to with a 95% of chance to get a better result with ESS over just N3 followed by BET. Here we also used another metric, Euclidean distance between the ground truth mask and the segmentation masks, the distance between the boundaries, and we had the same result. And also we penalized the borders that fall really far from the ground truth by square of the mean Euclidean distance. And we saw that in this case, ESS by reference voxel had the best result in for free images, and the other ones, the better result was with BET and free and BET. About time, that's a really good question. If you wanna just make a screw stripping and you don't worry about the cortex region, okay, use BET. It's much faster than you use the other approaches. But if you really care about the result of your segmentation, or if you need to make the inhomogeneity correction for post-processing, you can see that the three approaches don't have a very different execution time in seconds. The mean value of N3 and plus BET is 20 seconds, and ESS approach with BET and free and BET had 26 seconds. This is not the same of N3 and BET 2 times. It's not the same time, or plus the morphological dilation and the other operations. Why it's not the same time? Because N3 here is applied over the brain mask, and this makes a very big difference. the N3 runs much faster in this case. Also, here we have a similar time using a different method that's very good also in resolving the problem. So what we show here is that time is not an issue in this approach, at least when you use two iterations. One, the first stripping correction and the second strip. We can conclude then from our work is that inhomogeneity correction deeply affects co-strippings in 3 Tesla MR images. So we must remake all the analysis. Maybe they are wrong. Also, we must consider it in future studies that we made in the area, that we make in the area. ESCS is a very good solution. It's simple, adaptive, and it's feasible. It's not very slow. It has a very good execution time. And for future works, we want to test on other methods, not just BET and not just N3 and reference voxels, and more extensive experiments to have a very nice analysis of this problem. Well, I want to thank you for your attention. Eu peço mascarinhas, professor.
Any questions?
Or is this a limitation of BET, for example? So can you show, for example, the pipeline where you have you compute the complement of the mass, right? Then you recompose the. Okay. Do you really need to go to step number 6, for example, using 5?
The only problem we have here is that if you don't recompose the image, you have strong boundaries here. The methods may take these strong boundaries as being the brain. That's the problem. Sometimes it happens. We don't want to have a gap here.
Is it strange? Because, I mean, image number 6, right? You have this false boundary around the head, right? And then you have the same kind of boundary that you are looking for between the gray matter and CSF, right?
That's right.
And if you look at image number 4, you don't have the strong boundary of the head. So, but the other one has the same intensity, right?
Mm-hmm. So you have some in some places you have a strong boundary, like here, because when you delete it, it doesn't go very far from the original brain.
So what I'm saying is that it looks like to me that the need to recompose the original image is more a limitation of the BET algorithm than of the problem itself. Because it looks like to me that it's easier to strip the brain, the skull, right? To strip the skull on image number 4 rather than on image number 6.
Yes.
So maybe you should look.
I wouldn't say that's a limitation, but I think the method was designed to run over the entire image. That's the thing. Probably that's the issue that they have when you have the input image as a almost stripped brain.
Brief question, because we are short of time. Can you give more details about your method for inhomogeneity correction?
Yes, and the reference voxel inhomogeneity method is it's based in white matter voxels of the brain. It looks for white matter voxels in all over the brain and use it as the intensity to be corrected. So, for example, this region here has those white matter voxels. The entire region not just the white matter voxels, will be corrected based on the intensities of those voxels. And that's a good solution, because inhomogeneity doesn't change very fast. It's yes, it's a slow, very function, as we can say. I just want to make just a brief pronunciation about our institute, my institute. The University of Federal University of São Paulo is now have a master program, and we are recruiting students. If you are interested, to the next year, the website sjc.unifesp.br have more information.